In this video, we want to derive what are called Maxwell relations. And these are connections where we relate thermodynamic functions such as energy, enthalpy, Gibbs free energy, or the Helmholtz energy, to the variables of pressure, volume, temperature, and entropy. What we'll discover is that some of these functions are natural functions of certain variables. That is true if we can write a simple expression that relates how changes in the function are accompanied by changes in the variables. Let's use the internal energy here as our example first. We can write the first law of thermodynamics in derivative form as du is equal to q plus w. Now we can express the work as minus p dv in the case where we're looking at the expansion or compression of a gas, and we can express the heat as T ds. Why can we do that? Well, that comes from entropy. Remember, we learned that the change in entropy of the surroundings is equal to minus q over t. So that means that in a reversible process, the change in entropy of the system is q over t. And so moving t to the other side, T ds is equal to q. That's where we get this equation, du equals T ds minus p dv. And from that, what we say is that since we can write an expression like this, relating changes in energy to changes in entropy and volume, that u itself is a natural function of those two variables of entropy and volume. If we take the partial derivative of a function with respect to its natural variables, we can recover properties of the system. For instance, again, using this as our guide, we can write that the partial derivative of u with respect to entropy is the temperature if you hold volume constant. That's where we get this equation, right? Holding volume constant means that this goes to 0, and we're left with partial of u with respect to s is equal to t. We can look at the other variable the same way and derive that the partial of u with respect to v is equal to minus p. And that's where we derive this equation. Remember, we do have to hold the other variable constant. So it's the partial of u with respect to v with entropy constant is equal to minus p. So all of the thermodynamic functions have relationships like this, and all of them are natural functions of certain variables. Do you think you can derive similar expressions? Try enthalpy next. Start with the definition of enthalpy. H is equal to U plus PV. And then from there, write what dH would be. dH would be du plus dPV. And making some substitutions, see if you can't derive a relationship that only involves two variables in the end. So pause the video, see if you can't derive that, and come back and check out the answer. Here's the solution. You see we can express dH as du plus dPV. Expanding that in terms of the product rule, we have VdP plus PdV. And now we'll make an interesting substitution. Instead of du, we'll just plug in what we've already derived for du. And in so doing, you'll see that you'll introduce TdS, and you'll end up canceling this PdV because there was a minus PdV in the du expression. So the boxed equation is what we're left with here in terms of the absolute derivative of enthalpy. If we take the partial of enthalpy with respect to entropy, holding pressure constant, we get temperature. If we do that derivative with respect to pressure instead, holding entropy constant, we get the volume. Now that you've maybe getting the hang of this, why don't you go ahead and try writing out an expression like this for the Gibbs free energy. Again, start with what G is equal to. Does everyone remember? G is H minus TS. Because delta G is equal to delta H minus T delta S, so we can write that G is H minus TS. Starting from that point, see if you can't do some algebra like this and derive what are the natural variables of Gibbs free energy and write the expressions for the partials. Pause the video and give you a second to do that. Come back and check your work. And here we have the result. Again, we can use the product rule to expand the dTs term into these two pieces. And again, like we did before, if we substitute in for dH what we had in the previous work, we'll be able to cancel out the TdS and introduce the VdP. So this is now our, in the boxed equation, our final result for the Gibbs free energy derivative. Notice that its natural variables are pressure and temperature. And we can write the partial derivative with respect to each of those variables. If we hold temperature constant, the partial derivative of G with respect to P gives us volume, and the partial derivative of G with respect to T, holding pressure constant, gives us the entropy. Finally now, we want to see what the Helmholtz free energy natural variables are. And if you recall the definition of the Helmholtz free energy, symbolized by an A, that's analogous to the Gibbs free energy, only instead of enthalpy, you use the internal energy. So it's U minus TS is the Helmholtz free energy. It's the constant volume version of free energy. So starting from there, see if you can make the substitutions like we've done here to derive the natural variables and the partial derivative expressions for Helmholtz free energy. Pause the video, come back in a second, check your work. Okay, here's the result. Since A is equal to U minus TS, we expand the derivative TS part, and we can, using the substitution for du, we'll be able to replace du, and when we do that, we will cancel out the TdS term and introduce the minus PDV term. So we end up with this boxed equation showing that Helmholtz free energy is a natural function of volume and temperature, and the partial derivatives are shown. Holding temperature constant, if we differentiate with respect to volume, we get minus the pressure. Holding volume constant, if we differentiate with respect to temperature, we get minus entropy as the derivative. Now, we haven't derived any Maxwell relations yet. That's going to be the next step. Now that we have these fundamental pieces, we can combine them together to develop our first Maxwell relation. And the way in which we do that is to pick one of the functions and express its derivative with respect to one of the natural variables, and then take its derivative with respect to the second natural variable, and then do that same thing in reverse order, because from the fundamental theorem of calculus, one doesn't matter which order you take the partial derivatives, you have to get the same expression in the end. And so if we just plug in, we'll be able to develop what's called a Maxwell relation. Let me go through this with the example of free energy. Look back at your notes, you'll see that the free energy expressions that we can use here are that the free energy with respect to pressure holding temperature constant is volume, and the free energy with respect to holding pressure constant is minus S. T and P are our two variables that are shown as X and Y here. If we put in the partial derivative with respect to G, partial derivative of G with respect to T in here, that's like putting in there minus S. And we're going to put this one in here, and that will be V. And we're left with this as the result. So can you follow the logic there? Literally, we're just making the substitutions into this formula where X is T and Y is P. And the function itself, F, is G. So by doing that, we now can relate changes in the variables to other changes in other variables. So the Maxwell relation, this is the first one we've derived. It says that the partial of entropy with respect to pressure holding temperature constant is equal to minus the partial of volume with respect to temperature holding pressure constant. We've been able to relate how a certain variable changes in terms of other variables changing. This is very useful. If you think about this particular Maxwell relation, if you wanted to know how entropy is affected by pressure, that would be a difficult thing to measure. But you could easily measure how volume is affected by temperature. You could insert the ideal gas law here, and you could get an equation for how volume is affected by temperature. And in so doing, you'd be able to derive a more difficult relationship between entropy and pressure. That's how these Maxwell relations work. Pause the video. See if you can't use the other functions. We used Gibbs free energy here. See if you can't use some of the other functions to develop the three other Maxwell relations. Okay, we all set to check our work now. So here I have at the bottom of the screen the three other Maxwell relations that can be derived by going through that same process. So at this point, we have a lot of equations. We've got the fundamental equations that show how derivatives of thermodynamic functions are related to their natural variables for such equations. And now we have, from those, 4 Maxwell relations. Lots of equations to try to remember. But a long time ago, someone came up, his name was Max Born. He came up with a mnemonic that can be used. And I'd like to present that because you may have to, at some point, answer this question on an entrance exam for grad school or the GREs. And there's a simple way of generating any of these equations that you might need. It's called the thermodynamic square. And if I bring up the square here and interpret it for you, this is a mnemonic device. And first of all, you draw this square and you put 2 arrows pointing in the upper 2 corners. Corners and the sides of the squares all have letters. The corners, as you see, are variables. The sides are functions. The mnemonic that is used for this is valid facts and theoretical understanding generate solutions to hard problems. That's true, right? Valid facts and theoretical understanding generate solutions to hard problems. It's a true statement. It's a good one to remember. And it helps us remember this mnemonic. VFT UGS HP. You have to ignore the and the to and just focus on the first letters of the other words. And then finally, you have to remember that in Max Born's day, they used a symbol F for the Helmholtz free energy, F for free energy. And it has later, in modern times, been changed to an A. Some people like that as a way of remembering it. Other people just remember the letters. Some people, I have had students say I could more easily just remember VATUGSHIP, which also gives you the letters. So now that you draw this out, how do you get the equations from it? Well, each side is a variable, and the corners that are associated with a given side give you the natural variables for that function. So here we're looking at h. Its natural variables are s and p. We'll look at u. Its natural variables are volume and entropy. And so you go to a side and you find the function, and the natural variables of that function are bracketed at the corners of that side. Now, how do you get the derivative expressions? Well, then after you've found what the variables are, the things that multiply those variables are in the opposite corner. Here we have enthalpy. Its natural variables are S and P. So it'll be ds, dp, but what's in front of each of those? Well, you go from the opposite corner to get what each thing is multiplied by. So H equals T ds plus V dp. So can you write out all of the rest of those? I didn't mention what the arrows are meant to do, but the arrow is pointing at the positive term, and the arrow is pointing away from the negative term. To see how that works, let's do the u. What would du be equal to? It's a natural function of volume and entropy, but the coefficient of the volume will be minus p because it's down here, the arrow is pointing away from it, and the coefficient of ds will be positive t. So you get du is equal to minus p dv plus t ds. Now we can go on and see how the corners are related to the Maxwell relations. So just take these two corners here, S and V, and on the other side we have P and T. And so one of the Maxwell relations is that the partial of S with respect to V is equal to the partial of P with respect to T. And so we can take corners like that and derive the Maxwell relations that we just did. It's a way of remembering them. Again, let's do that one again. Partial of S with respect to V. There I've used the two corners here, and now in the same order, P over T. That has to be equal to partial of P with respect to T. So there's the equation with the things that you're holding constant written correctly. Now again, you have to watch the signs. So we took the corners that are basically vertical here. If you take the corners like the bottom and the top, there's equivalent Maxwell relation, but there's going to be a sign change. And so let's do S over P is equal to V over T. That is to say, partial of S with respect to P is equal to the partial of V with respect to T. Except we're going to need to put a minus sign, and then we can add the things that are constant. We put T and P there. And that will give us, from the thermodynamic square, another Maxwell relation.